Nice. I was wondering, have you moved from Netherlands to
Yes,
Poland?
yes, 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 yes,
Super.
yes. Then I moved from Netherlands 2020, end of 21, when the pandemic was high. We were also we closed offices in Bercho for 8 months, at least in our Dutch part, and therefore I said, okay, we are locked in the house with kids anyway. Maybe we go to see family in Poland, and I will work from there, you know. And I start to work from home, and then after a couple months, kids went to kindergarten here, and then I was still working from home. And one moment, of course, we opened the office, but it was kind of like 1 day a week. Then I said, okay, it makes no sense to come back for 1 day a week. And then in the end, I, after 1 year, I was not able to move back because we already organized everything here. Then I said, we need to sell our house in Holland and move to Poland because kids were, how to say,
Yeah.
kids were really bonded with grandparents. They didn't want to move. And I said, okay, now also with remote work, you can do a lot. And I said, okay, I will then do something else than Berhof. I will do some consulting. I will work on different projects. And also it was good for me to clear my mind a little bit. I did like half-year break, then I didn't do any work, only just moving to the new apartment, renovate, doing some simple work like labor work, but not at paid, but at home,
Yeah.
and then just to clear my mind what I want to do. And then after some months, I had companies from United States asking about this, about that. And I said, okay, good. I was out of business, but now I will start a company. I help you. Then basically, even the starting company was not first. First, I had some customers which say, Piotr, can you help me? And then I said, oh, but if I help you, then I will get paid. And how we would deal with this? How we deal with this? And in the end, it was okay. I needed to start a company, and therefore we start Aqua Azure.
Oh,
You know,
interesting.
and in order to basically facilitate the work what I had, but I also was a little bit more, how to say, not strict, but a little bit more focused my interest where I want to go. Therefore, we had this discussion before. Water is related to water. Then I love water still, and I love let's say the renewable energy related to water, and therefore the energy and water I wanted to mix together. And this kind of projects I'm now busy with. Then what we do, then we focus mainly on water and let's say water-based systems for energy generation, energy storage, and this is also where my passion is, and this is where we will be building and going from there, let's say farther. But everything related also to save, to help this energy transition. Now we are facing going from fossil fuels to, let's say, sustainable energy sources, but we want also to help the planet to make this environmental impact lower, with, let's say, moving from fossil to via this decarbonization or via this hydrogen. But hydrogen, we're not there per se, but we want to deliver the water to be able to split to hydrogen. Therefore, the company was born, yes, and not by accident, but at least that from our passion, from my passion to water, energy, and this is what we are now focused to do. And we are on the beginning of the journey. Then it's still the systems and the work what we do. Then we are now putting a lot of ideas into the products or services. And besides of this, we also do consulting. That if I have some companies related to even filtration, like what I did in Berhof, or the smart software, then I help other companies to do consulting. But in the end, we would like to focus on the systems and support the industry.
That's really interesting. I mean, when I get your recent published articles, which is kind of energy from waste heat, for me, it was very interesting. I never heard about a reverse electrodialysis system.
Yes, it is not very well-known system. It's now two companies are focused on the system. The one company, it's in Denmark. It's called Salt Power, and they're using pressure retarded osmosis, which means that they do reverse process to RO. Then they have two salinity streams, and then generate a pressure. This pressure runs the turbine, and they generate electricity. And The other company, Redstack, they basically follow up on my PhD research, because this is this reverse electrodialysis process for energy generation I did on my PhD 4 years. And once I finished, then Redstack company want to commercialize. They acquire some patents, they acquire technology, and since 2009, they commercializing this technology. And they focus mainly where river flows to sea. Then you have, then you have river, which is low salinity, you have seas, higher salinity, and you can generate energy there. But what is really interesting, that it's not very common, but now it seems to be more recognizable. I saw that they had a meeting with European Union in France, and they promoting this osmotic power. This called osmotic power. They promote this type of energy because you can produce it basically 24/7. It's not like wind or solar. You need only seawater and fresh water, or at least river water, or different in salinity. It can be also Dead Sea and just other sea. Wherever you have different streams in salinity, then ions migrate through the membrane and electrons start to flow. But energy density, in my opinion at least, it's still quite low. Then basically, if you have a membrane, then per 1 meter or square meter of membrane, you produce between 1 and 2 watts, Then you need, in the end, for 1,000 square meter, you have 1 kilowatt to 2 kilowatts. Then you need square kilometer of membrane to produce megawatts. Therefore, this is where they are still developing,
Yeah. But in your case, this heat is involved. Could you maybe lay out the technology here?
Yes, then this is exactly the same system, Then you have still, you have higher salinity stream and lower salinity stream. And what you do, you play with the heat, you basically playing with solubility of your salts. That if you cool down certain salt, it starts to precipitate. And this means that if you precipitate the salt, you have, let's say, lower salinity concentration. And this precipitated salt you can add to the higher salinity concentration. You can have closed loop system, but only reheating or heating and cooling solution. And by heating and cooling solution, you're playing basically, you're delivering the energy, but it can be also waste. If you cooling the building, you're bringing this heat out, and you can use it to let's say, heated up solutions to have higher solubility, or cool down, lower solubility. And by playing with this temperature, let's say temperatures, you can precipitate the salt. And basically, that's the main principle of the system. You have highly concentrated stream, and let's say with a low concentration stream. And to regenerate the driving force of this process, you basically lower the temperature in one solution, you precipitate the salt, which is precipitated, you add to the highly concentrated solution and do the process again. And by combining this with heat pump, you can very easily at the same time cool and heat, and there's no problem, because normally the big heat pumps, or sometimes, cooling towers, different system, but big heat pumps are installed in the industrial objects and so on. And the goal of this system was at least to have, at least, but it's a big word, because they aim to have, I mean the company which I work for, this is Halocline International, they aim to have net zero cooling and heating. That the energy what they generate, they want to run the compressor which cools and heats. And if you have very efficient heat pump with a high COP, then you can do it. And they are now in the phase to build the pilot and demonstrate it. That will be very interesting application, that you can at least do something with this waste heat, because normally you cannot do so much with this. There's a lot of terawatts of waste heat. It's going to the atmosphere, and of course, some industries are using waste heat to heat up the buildings, but it's very, very uncommon, to have this installation. And this installation can be small. It can be even for smaller industries to generate at least a little bit electricity back to run your heat pump, to have more efficient process, to reduce some CO2. Then this is at least the first step to have this system, let's say, built in such a way that we can reduce the amount of energy needed for heating and cooling of the building. Ideally, if it's going to generate as much energy to heat and cool at the same time that you are, let's say, net neutral. And then the goal will be, for sure, if you can generate electricity on top of it, that will be great. But it's step-by-step approach, and I think we should also take it as it is.
Yeah, in terms of, I mean, I did quick research for the reverse electrodialysis. In terms of, let's say, science, is there something need to be done still in academia, or let's say in R&D perspective to make it feasible?
Yeah,
let's say?
yeah. Then I would say then this technology it's commercialized, but not to the level that it's widely applied. Then, for example, why it's not applied? Maybe this, and what are the challenges? And the main challenge is the membrane price, because ion exchange membranes, if you the same membranes used for electrodialysis process and other processes like continuous electrodeionization, and these membranes are quite expensive. They range from, let's say, 30 euro to 150 euro per square meter. And in order to have this process economically feasible, you need to have a membrane below 10, ideally 5, maybe the best will be 3, but very cheap. But it can be also very thin membrane, because the conditions there are not very harsh. Then you only transport salt from one side to the other. You don't push high currents and so on. Therefore, maybe membrane can be thinner and can be more economically feasible. That's for sure the one challenge. And the second is to build system in automated way, in my opinion, because if you have 1,000 kilometers of membranes, you would like to have system which can be automated and built by robots.
Yeah, Piotr, you have, I mean, decades of experience in the membrane. So based on your experience, I think we know that, let's say, the producer of this reverse electrodialysis, they're not the one who own the membrane. They're not the one who developing the membrane. They buy the membrane, they assemble everything. So based on your experience, does those guys need to have a know-how in order to tune the membrane, or you think it's enough? The ion exchange membrane exists in the market, that's enough. They need to improve, as you said, electronic and other stuff in the system.
It is a little bit chicken and egg,
Yeah.
And for example, this ion exchange membrane, indeed, it's evolving. Then we were starting from electrodialysis systems. Then I was also developing this membrane capacitive deionization system for treatment of brackish water. Then you also need this ion exchange membranes. And the big drivers, I think the ion exchange membranes is relatively small and needs to grow in order to reduce the price, And if we look now, also fuel cells push the market farther, which is good, that you need a proton exchange membrane, which basically is a cation exchange membrane based on fluoroplastic, this PFT backbone with sulfonic groups. But what is really great that now fuel cell technology is pushing the price down, because this is where manufacturers also focus and volume are greater. Then you have now to hydrogen electrolyzers, you have proton exchange membrane electrolyzer. You have also now new, it's not relatively new technology, it's an ion exchange membrane electrolyzer, and also membranes are there. Bottlenecks, they will be different chemistry membranes. They need to be very robust. However, there also is a larger need for ion exchange membrane. This means that the market is growing, and also by developing this market further, applications like reverse electrodialysis will benefit, because there will be more companies, larger knowledge, and so on. But if you look on this application, you need big players, because you need square kilometers of membrane. It cannot be small players. And I know there were some partnership between, let's say, Red Stack and Fujifilm. Fujifilm in the past, they produced film for cameras, but now they focus to produce membranes, and they were quite good in this, and they can make also square kilometer of membranes, ion exchange membrane.
Are they really focusing on ion exchange membrane?
Yes, they do.
Okay.
Yes, they do ion exchange membrane. When I was finishing my PhD, they were already stepping into this field. They were learning quickly, but now they have in their offer ion exchange membranes. And that's also good news, because you have big players there. They can make large volumes, once they start production, large volumes. But I would say this technology will evolve further. It will probably first find its niche applications where you can generate electricity from a large difference in salinity, maybe like harvesting this external or waste heat, because then you can play with your salinity gradient. It doesn't have to be seawater and fresh water, like gradient between, let's say, 30 gram a liter and 1 or 2. You can create artificial solution with large gradient, and then by doing this, you can go from 1 to 2 watts per square meter. Maybe you can go to 5, 7, and that becomes more beneficial. You can harvest more energy. And indeed, this ion exchange market is developing, and I see the reverse electrodialysis will be there. But where and in which application it will end up, that's what we need to see. But it's at least good that is developing. Then you can see big progress from decade to decade,
Yeah, if I understand correctly, reverse electrodialysis has far better advantage compared to pressure retarded reverse osmosis in terms of generating energy on the footprint, let's say.
I would say they are similar technologies, but then you need a high pressure to convert this to electricity. You need extra step. Then you have two salinity difference, and then you build up the pressure, and you need to turbine to convert. Then you have extra step. Electrodialysis can do it directly. However, how I see it, that reverse electrodialysis, it's more applicable to more intermittent application. Then you stop quickly, that it can start quickly, stop quickly, and let's say small to medium-sized application. And when I see Pro, it's like RO systems. The huge systems, many modules, combined with 1, 2 turbines, bigger turbines to convert, working 24/7. And this is where I see this technology. Therefore, you have different application. Let's say large system application, which is Pro. At least I see it this way, and reverse electrodialysis for the smaller and medium systems.
I know that the ion exchange membrane, as you mentioned, it will open, or it will help so many applications, and one of them, as you mentioned, reverse electrodialysis. So based on your experience, if we look to the market, we find few players. I didn't know Fujifilm. I was aware only of 2 players in the world who really take the big share in the markets. And my understanding is it's difficult to produce chemically and difficult to control the chemistry of the production of this ion exchange membrane. Is still so, or do you think the market is improving a lot that could be synthesized differently? Recently, I'm not sure if you are aware, there is kind of silica-based ion exchange membrane, which is really interesting to have silica.
Yes, I heard about this, that it's silica-based ion exchange membranes. But it is the backbone,
Yeah.
And the membrane stability, it's always related to the group which you use, and indeed how you locate the group in the backbone. And in many applications, what I have seen from my experience, that an ion exchange membrane is a limiting factor because it's less chemically stable than cation, which is based on sulfonic groups. Here we have quaternary ammonium groups, and the whole challenge is to make 2 membranes, let's say, stable. But in order to have this couple stable, then anion is a bottleneck. Then the companies which produce good anions, then usually they have high quality application, like in fuel cells or this electrolyzer, because they can apply this. And this is the challenge. They indeed, big players figure it out, and the small players going there. Then the small players need to make their membranes more stable, more robust. However, it depends on the application, because if you have an intermittent application that you generate maybe a couple hours per day, this energy to have some energy return, that might be fine to have lower quality membrane, but also low cost. But if you plan your systems will be working 24/7, then it's better to have high quality membranes. Or if you have application such as like fuel cells or generating hydrogen, then better your membrane is high quality, because this is what you need for continuous operation. Then there will be some difference between, let's say, these applications for fuel cells, hydrogen, and also water applications like electrodialysis to separate solution, especially high quality, that your membrane has low leakage, low water transport, and application like where the membrane such is not as critical as in other applications like reverse electrodialysis, because then we need to focus on the resistance of the membrane with acceptable selectivity. Then if you have 90% selective membrane, then you say, okay, it's great, but we need very low resistance, maybe half ohm times square centimeter. But if you have, let's say, membranes for, let's say, high quality application, high separation application, then you need to be as selective as possible, 98%, 99%. And the resistance is secondary because you can put a little bit more power to push the ions through the membrane.
It's very interesting. I mean, I like the way how you frame it, which is there are different applications and each application has different operation, some extreme, some okay. So you need to really know where you are going and
Yes,
what is
exactly.
expected from your product to deliver, because some applications really they need high quality delivery, as you mentioned them.
Yes.
And is it something that you offer in the consulting of Aqua Azure, that you guide if even new startup company to know which application, which market is the right for you at the moment?
Yes, this is exactly what we do. We advise companies for their application, what kind of membranes they can use, what kind of spacers. This is the spacers between membranes and promote the turbulence that it can also improve the performance of the system, what to use. And in general, for their application, what they can use, what is the most suitable. Then this is what we advise the companies there. And this is also our expertise, or at least my 20 years experience with ion exchange membranes. And for different applications, you need different membranes, as you already mentioned. There are also, I will go a little bit to a very interesting new application. You can also use ion exchange membrane in this ionic flow batteries. Yeah. That you have two solutions also, and you push the ions. Let's say you have two solutions, let's say 1 cubic meter of one cubic meter of other, and you push the ions from one solution to the other, and this is your battery. This is your battery. When you charge the battery, you just have one depleted solution, one concentrated. And once you release the ions back, via, for example, this reverse electrodialysis system, you can have your energy back. And the round trip efficiency, it can be still 70, 75%. It's not 95 like lithium ion, but you still can store some energy, and even for longer time, which is very interesting. Then this is ionic flow batteries, like systems where you push ions based on reverse electrodialysis. You can also have redox systems, which you on electrode change valency of the ions. But for me, it's very interesting that ion exchange membranes can be applied also in this new application for energy storage. Especially it's now important now when we have more solar, we have more wind energy. And when it's a peak wind, it's great, but you need to store this energy somewhere and deliver when it's the demand. And this is where also this energy storage systems can support, especially solar and wind installation.
Yeah, and the battery that you mentioned, I think it's very interesting. And one of its challenge, if I'm not mistaken, is the temperature. I mean, if you would use that in a desert of Africa, it's still critical high temperature for those. They still didn't solve this bottleneck. I mean, it goes up to 60 or 70 degrees.
Yes, and this is also mainly because of the ion exchange membranes. Then indeed, this application is now, we try to push this, and with the project which I had with this American company, Halocline International, which they use waste heat, they also want to go as high as possible, because then you can use this solubility gradient. Then you operate high temperature, cool down to almost zero, precipitate, and again go back. And this is also what I think the challenge at front of ion exchange membranes, how we can operate these membranes at higher temperature, higher than 60 degrees. And I think in general for all polymeric membranes, even if you look on ultrafiltration membranes, nano, to push harder. Maybe this, what you already mentioned, this silica-based membranes, they can be very firm and stable at a higher temperature. But also we need to keep in mind that the degradation ion exchange groups accelerate, that each 10 degrees, it's double, that if you operate your system at 20 degrees, then your lifetime will be twice shorter at 30, and again, the double from 30 to 40 and to 50, then you might reduce your lifetime of the membrane operate at high temperature. But I believe that this is the challenge, and this is the challenge which we should solve in future to operate at higher temperatures, especially the membranes, or develop some ceramic membranes, ion exchange membrane, which can operate at 80, 90 degrees, maybe even higher.
Yeah, I mean, you think it need to be fundamentally solved, I mean, from the science standpoint, to make a really stable ion exchange membrane. So you need to go really deep to solve this point, I think.
Yes, yes. And this is not now. Then this is a challenge maybe for next generation, or at least next decade, but it's not solved now. But at least we are learning where we can apply current materials, what we can do with them, and what are the limitations. And we need to be aware of it.
According to my knowledge, Professor Ivo Makelikom, he is working on this project. I think they call it the Moonshot project in Europe, to really fix the chemistry of those ion exchange membrane in order to be stable at high temperature. It's really challenging. As you say, this could be for the next generation to really upscale it and to make it real industrial scale.
Yes. It will be great to have this membrane.
Yeah. Now we move to the hydrogen production, which is one of the things that's also fall onto your expertise.
Yes.
You have highlighted the importance of water hydrogen production. Would you just give an idea why water is crucial for this process? I mean, why is the quality is very important for this process?
Yes, I will explain this, but maybe we'll go back. Let's say in Europe, we were running mainly on gas, and we have also a lot of gas from Russia, and it was no problem. But since, let's say, this all operation in Ukraine started, we see that it's huge demand for, let's say, sustainable systems where you can generate hydrogen. Some countries adding even hydrogen already to their standard methane gas for the household, and some other countries are planning to do. Then there's around hydrogen, it's a big hype. It's a lot of money also available where they put to different systems. You have you have standard alkaline electrolyzers, which are working from decade. Now you have also the new electrolyzers to produce hydrogen, which is this based on proton exchange membranes. Then new technologies going to also an ion exchange membrane-based electrolyzers. But when I see LinkedIn or social media, everybody talks about hydrogen production, but not everybody talks about water for hydrogen. And this is where we saw our opportunity to say, okay, our expertise in water. And this is where we see our opportunity to really go deeper into the water, because if you want to produce hydrogen, let's say 1 kilogram of hydrogen, you need at least 9 liters of water. Let's assume it's even 10 to 1. Then for 100 tons of hydrogen production, you need, let's say, 1 million cubes of ultra pure water. And this is very important, because if you look now how much petrol cars tank per each station, then if you think about the hydrogen, okay, it will be hydrogen production in situ, it will be delivered, we need to think about this. If we will be even power our cars with hydrogen, how much water we need to do it. And this will be ultra pure water. It has to be very high quality to not destroy electrolyzer. If we look on alkaline electrolyzer, quality can be a little bit lower than this membrane-based systems, but still we look on very high quality water. And this is where we see our opportunity to look on the systems which can basically treat water from groundwater. We also look a little bit into the rainwater, because it's coming from the buildings and you can treat it. You can also look on the cooling tower water to produce hydrogen. And why it's important, because we even see some companies, they designing, let's say, heaters for household, just central heating for household, for industry, based on the hydrogen systems. That if you can make a system more robust, more sustainable, where you can collect the water or some cooling tower water pre-treated, and you can use this water to produce hydrogen, then you manage your waste. That's one. And secondly, you have water easily available. And you need a lot of water. That's already we have spoken. But for producing this 10 liters of ultra pure water to produce 1 kilogram of hydrogen, you need at least 15 liters of groundwater. And if you look on seawater desalination, then from 15 liters of groundwater, it's becoming 35 liters of seawater. That if you pre-treat, or at least you want to make your ultra pure water from sea once, it costs you much more, because it costs you around 7 kilowatt per cube, compared to, let's say, 2 if you do it from groundwater. But you need to waste much more water to just produce one kilogram of hydrogen. And it's great that we look on it, but we also need to be smart about this. We need to look for what kind of sources of water we have, because even now we don't see water as a scarcity. Of course, some countries already have problems with water, and we see that they have big problem. But if we want to shift to this, let's say, energy transition from fossil fuels to hydrogen, then the water will become even more important. This is what we look, and we look where we can treat the water, let's say, low-hanging fruit, that we will not do seawater desalination with the cost, which you need to use 3 times more water and 3 times more energy than, for example, groundwater. We look what kind of solutions we have there for rainwater, we look on different wastewater to treat it and provide the system which will be able to treat it to such a quality that you can use in your electrolyzer, And this is only about ultra pure water for hydrogen production. And in this process, you still need the cooling water and so on. Then this is much more than this. But at least we see that there will be a very important topic to address.
Yeah, I mean, roughly, have you done the calculation to estimate how much you need for 1 gram hydrogen, the total water?
You need, depends for what source, but you need at least double the amount. That if you have stoichiometric, it's for 1 kilogram, you need 9 liters of water. I think you need to double it, at least 15, 18 liters from groundwater or wastewater,
Yeah. Does this make sense, really? Is it the optimal way to store the energy?
I don't know if it's optimal way to store the energy, but if you look on fossil fuels and to run your cars and so on, I think that this is a good solution. I'm not sure if it's the best solution to store energy, because if you compare, for example, lithium-ion battery, if you look on the battery side, let's say if you have lithium-ion compared to, let's say, hydrogen storage, the lithium-ion is between $200 to $400 per kilowatt hour stored. And if you have the system based on hydrogen storage, it's more than 1,000. That you already see that the factor is 3-4 times higher than lithium ion. Then if you want to store energy, this is why we also look on these ionic flow batteries, because they are more expensive than lithium. They require a little bit larger volume, the footprint, but they still are cheaper than hydrogen. Then I think if you look on hydrogen, it's great to be used. I don't see that it's a great solution for the energy storage, but I think it's a great to produce and use it.
You mean it's not great from the money standpoint, and also from the sustainability standpoint, environment, I would say.
I think if you have other systems to store energy, maybe they will be more suitable to do it. But for hydrogen, I see it more as you produce it, you compress it, and then you use it. I will not do storage because you have also this leakage of hydrogen, You need special tanks. The whole storage is difficult because you need to dehumidify the gas, you need to compress it hard, you need to store it or transport it. Then this is, and then you store it in very large pressure, And this, for me, sounds like not safe and not the best way to store energy. But therefore, you have these battery systems, in my opinion, or a water battery or redox flow where you can store energy. And hydrogen, once it's produced, compressed, should be put in the cars or put in the factories in tanks that it can be used to burn and to heat it up, or use it to as a heat source. Then this is what we believe. Therefore, we look on this also. This water for hydrogen is one. Okay, great. Then you have also these batteries where you store energy, which can be a redox flow battery and so on, to support the system. We actually want to support this energy transition, what we see now. But my belief, at least for now, it's hydrogen is great for transportation. It's great for the buses, It's great to remove the fossil fuel combustion in the cities, that you have clear city when the buses are running in hydrogen. Even private car, you have Toyota Mirai, I believe, they also run on hydrogen. That might be a very good solution to run your transportation, to power the production. For the steel factories can run on hydrogen, to heat it up, the ovens and so on. That's a great source. If you can remove gas and provide much more hydrogen, then it will be great. But I don't believe that it will be only purely for energy storage.
Yeah, and there is so much focus also on lithium battery. I'm not sure. I didn't search. Do you have any rough idea about, in terms of sustainability, how much water you need in order to extract lithium? Because I know the mining, they consume so much water, and they are wasting.
Yes, I wrote a post on LinkedIn for our company, for Aqua Azure, and I had these numbers, but those are large numbers. I don't know by heart.
So it's still not sustainable compared to.
No, but you have evaporation ponds. I think this is the cheapest way that they extract lithium, or from brine, they do this evaporation ponds. They need to extract that. It cost, and lithium, I think last year, I don't know, it was per ton, it was $80,000 or something like this. Now it went to 28, 30,000. Then the lithium becomes more rare and rare, and depends how much mining will be done, how much companies can explore. I don't know even if we have enough lithium to have all the batteries which we want to have. Then even besides of water usage, which is enormous, I don't know if it's enough lithium. Therefore, we're also looking on alternatives which can still compete with lithium in certain application, like this vanadium batteries, because lithium is great, I think, for the laptops, mobile phone, and so on. But is it really great to store energy? For example, like you have trucks or buses, or maybe this battery will be run on hydrogen.
Yeah. And I mean, focusing on hydrogen. So what are the primary challenges in using water? I mean, especially non-traditional sources like brackish and wastewater to produce hydrogen. I mean, what are the challenges, and how Aqua Azure is addressing those challenges, for example?
Yeah, then there's lack of knowledge. That's the first challenge. Everybody knows that the water for hydrogen needs to be ultra pure, but not all. It's not lacking the knowledge. It's lack of the knowledge, basically, to see how big impact these impurities have on the system. At least there is some knowledge that we know these alkaline systems are more robust than this membrane-based system, like proton exchange membrane and anion exchange membrane. But there's also lack of knowledge. For sure, there is known that the 65% of system failures, loss of performance, it's basically related to the water quality and contamination of water. And where we're talking now, we're talking about water which going to electrolyzer, but also we are looking into the water in circulation. If you have inside the electrolyzer, you have other loop which circulates the water. And this is very important loop, because if you deliver ultra pure water, it will suck out all the ions, everything from let's say, we have system with stainless steel tubing, then iron will be for sure pulled out from the tubing to ultra pure water, and this iron can poison your electrodes. Sometimes you have also sealants, which you have ultra pure water, and you have some sealants, and then ions or some impurities are pulled out from the sealants into the, let's say, electrolyzer water. And what is very important to understand, that the water which you produce hydrogen, all impurities will magnify, because you produce hydrogen. The water stays there, it becomes oxygen and hydrogen, but impurities stays there and concentrate. The longer you operate, they concentrate. Therefore, we also look on the water which is delivered there, but also water in the loop of the system, inside the system, which is very important. And this is water, it's important for membrane systems, like a proton exchange membrane, that you remove some impurities which are not, let's say, exogenous from outside, but from inside the system, from sealants, from tubing, and so on. That this is also kind of like a safety loop to remove any impurities which are in your system.
So what is a perfect system looks like to really tackle those things? It should be very expensive, I think.
Yeah, that's the problem. The systems, it's always about the balance. If you don't invest, in system and purification loops at front, and a good purification system at front and the loop, then in the end, your system performance is decreasing and you need to replace, And even if you have I will give you some very interesting example. Even if you have perfect system and you have alkaline electrolyzer, which is running on potassium KOH, potassium hydroxide, this potassium hydroxide sometimes have impurities. That if you have this potassium hydroxide order, it can be impurities, can be very small, 2%, 1% or lower ppm level, but they will concentrate like iron or cadmium or other impurities which are not listed there. You order it, they say it's 98, 99% pure. But what about this 1% or 0.1%? This will contaminate your electrodes. This can contaminate your membranes even. Then therefore, if you look on this whole system, even if you say, okay, this is a perfect system, and you order sodium, not sodium, but potassium, let's say KOH, and you make the solution, you make an alkaline solution, and then you have some impurities. What you do about this, and that's important to also look for this, let's say, whole process side. System is great, but also look on the process where these impurities can come from, And also, what are your electrode materials? Are they leaching or are they not leaching? There's a lot of in design way, but at least I think with the best balance is to have, let's say, relatively robust system and water system, that you protect your electrolyzer and you keep on running, and then you see what are the bottlenecks, because as you know, currently membrane are also bottlenecks there. It's a proton exchange membrane. You have also an ion exchange membrane, which they need to improve in order to reach a higher lifetime of electrolyzer. That if you look on electrolyzers based on the membranes, the lifetime is lower than a standard old school alkaline.
So roughly how long is this? How many?
I think this alkaline ones, 10 years, they can reach easily 10 years.
Okay.
Then those are the first one. But if you look on this proton exchange membrane electrolyzer, maybe 5, 7, depends on the system design, depends on the company, because we're not building them. But if you look an ion exchange electrolyzer, then the lifetime seems to be the lowest. Then we have the more mature system around 10 years, even can be 15, depends on the application, depends on the loading. And the SPEM, it's emerging technology, proton exchange membrane electrolyzer, which still needs to be improved, but it's getting closer and closer,
In which way it still needs to be improved?
I would say in stability of the system, and membranes, and also improved in terms of just operational hours, There's not so much data available for, let's say, full-scale commercial electrolyzer. I think now we are going to this phase that the companies will start probably big commercial system with alkaline, and they want to move to the newer technologies and see how these newer technologies can perform. Because if you look on alkaline, let's say, the higher performance, which is proton exchange membrane, can deliver you, let's say, the system can be twice smaller to deliver the same amount of hydrogen. Can operate at higher currents to produce the same amount of gas, then it can be smaller. Then it's already an advantage of this new system. But also the life cycle needs to be assessed. What type of membranes? How we can make this membranes tougher? How we can make separators, electrodes? I'm not sure if even stronger, but in more sustainable ways. In this proton exchange membrane electrolyzer, you use a lot of precious metals, and you also don't want to use them. Then therefore you'd like to have electrodes from more sustainable metals, Then this is the trade-off what we need to look at.
So which kind of, I would say, customer or kind of application, generally speaking, that you are seeing are more, let's say, taking the risk to adopt and play with this reverse electrodialysis system? Pharma industry, or so which one is really, you think they take the risk and really they're doing a good job to understand?
What do you mean for hydrogen production?
Yes.
Or for energy?
For hydrogen production.
For hydrogen production, I think we will start with the systems which are already from decades, this alkaline ones, so which you have standard separator, it's Iraflon separator. between the electrodes. It's operated base solution basically, and this will be first generation, you know. And in meanwhile, when you have this first generation, then the companies are already working on generation 2, generation 3, which means that those are the membrane systems. Which will be better? I don't know, but this we will find out in coming years. But this is regardless which systems we use, they will differ from each other based on applications, like you mentioned, and the volume. Maybe for industrial you use alkaline, maybe for small volumes you go for this different other systems. But for each system you need to still deliver the water quality. This is where we focus more. It's not about the system. Okay, if customer has this system or company developed this system for, let's say, alkaline, we focus to deliver the most suitable water for alkaline system in order to protect it, that can run longer. And if we have the system based on the membrane system, we will be ultra cautious that we need to look in the water in certain way that we remove almost all impurities from feed, but also we're running this loop for any contamination. You know, then this second generation systems are more sensitive, but therefore we want to protect them a little bit better. And which technology will win? I don't know. But at least I'm happy that they already starting this initiative with hydrogen, and we promoting this energy transition. Especially when I live in Europe, you know, we have energy scarcity. We don't have energy storage. In summer, it's great, it's warm and it's perfect. But in winter, we have less sun, we have very cold weather, and then we need energy storage. Then we need, you know, hydrogen, maybe to power our cars. And this is what excites me, and this is also my passion to develop the system, to see it still the system running, and to see the cars running on hydrogen, that you don't have this old diesels. You know, putting a lot of smoke in the air, but you have hydrogen cars, which you only have pure water going out of your exhaust pipe, or at least exhaust tube.
Exactly. And if I look to the market right now, I would say, roughly speaking, there are two that I'm aware of, two big OEMs who are able to really to produce green hydrogen by using the whole system. The whole technologies, combining different technologies. And actually one OEM and the second OEM is combination between two kind of OEMs in Europe. So why do you think, or that's not so many OEMs is stepping up into this green hydrogen production? Is it so complex? It needs so much investment, or?
Yes, you're exactly right. It's complex. It's a high barrier to enter. It's because you need specialized knowledge. You know, you need specialized knowledge about materials. It's also very expensive, even to build such a system. It's expensive. You need electro specified knowledge. Therefore, there are not so many. And I think the market is not picking up yet because you don't have commercial systems already installed. They are starting developing. There's a lot of money flowing. But are these two big OEMs, are they making money on these systems now? Do they can be self-sustained and invest in this, you know? Because once the companies will make a profit and invest and governments support them, then we should see the boom, you know? But that's a good question, at least now. I hope it will accelerate this trend. But I see we are on the beginning. Then my feeling is that if we are now 2023, 2030, we see much more companies, and maybe 2050, that will be like, you know, Shell will have own electrolyzer on the petrol station running from different water sources, you know, British Petroleum the same. That might be the future, you know, that we will be generating hydrogen in situ from wastewater, from rainwater, from whatever water, that it even will be closer loop, that your fuel, it's only will be, you need energy to pre-treat, let's say, wastewater, and then you can produce, and you need energy to produce hydrogen, and then you have your fuel. That will be my dream, where we can do it, you know, that we are not limited by amount of fuel transported from the ground, but we only can run this with green energy, because that's important, you know. Also, we're talking about green hydrogen, but green hydrogen, it means that it's produced via electrolysis from sustainable energy sources like solar, wind, you know. And I would like to see it.
Yeah, I think maybe the reason why these I'm not sure if they make money, but I think the reason why they are the leaders because they just leverage the know-how that they generated with non-green hydrogen, just hydrogen production. Because as you mentioned, hydrogen can be green, you synthesized by using renewable energy, can be also, I don't know what they call it, just standard hydrogen, or I don't know.
I don't know. There's a gray hydrogen,
Gray
purple.
hydrogen. There's so many names, yeah. From
yes.
fossil fuel, they produce it, as far as I know.
Yes, yes. And this is, for example, now I moved to Poland, and then you see the electric cars and people say, oh, great, I'm running on an electric car. But 70% of power is made from coal. That even if you have electric car, zero emission, it's written zero emission, the the electricity which is made to run your car is 70% from coal. Then I think that we need to change our thinking. It's great to have electric car once the energy is generated from sustainable energy source, and that will be perfect. But I think we are getting there. It's good to bring this awareness. It's good that the companies are starting thinking about. I think if governments helping to push this forward, then we can build sustainable future.
Right. And and one thing, Piotr, if you can, just for the audience, the one who are not familiar with the redox flow battery, it's just clear definition how it works, basic terms. I mean, roughly an idea how it works.
Then redox flow battery, it works that you basically have reduction and oxidation reaction. And if you have, let's say, vanadium ions, then you can reduce, let's say, from 5. It has 5 charges, positive charges, it's +5 charge, and you can reduce it to 4+. Mm-hmm. This means that always if you reduce valency of the ions, electron needs to be transported. That basically you have a certain amount of ions in these solutions, and you reduce valency of one ion on the electrode, and your electrode is transported to the other side, and you increase on other side valency of the other, and therefore you have 2 different tanks, 2 systems, and in one tank you reduce the valency, and in other you increase, you oxidize. And this redox flow battery too, in simple terms, because I see it's not easy explained from my side, but in simple terms, you are playing with the valency of the electrodes, of the not electrons, but of the ions, and this is related to electron transportation. In order to increase valency, electron is negatively charged, and if you want to go from, let's say, 4 plus vanadium to 5, then you take 1 electron. And this electron is transported from cathode to anode, or vice versa, and generate this electricity. That you need to first invest electricity to charge your system, to change valency for, let's say, higher, and other solution lower. And in order to harvest this energy, you do it in a simultaneous way, that you not shortcut, but you apply some load, and your system wants to go to balance. That everywhere in one solution and the other solution, the valency will be the same. This is like an electron neutrality principle. That system wants to go to the same amount of charges on one side on the other. Therefore, if you charge one tank, let's say, will be on higher valency, other on lower, system want to go back to the balance, and therefore electrons are transported. It's not easy to explain me in explanation. You need to basically do the redox reaction, that one ion accepts electrons and other ion leaves the electrons, and this electron transfer generate electricity. But first, you deliver this electron from your power. Then first you put certain amount of electrons to charge the system, and then you can have electrons back. And the same with lithium-ion batteries. You do exactly the same, but this lithium-ion batteries, if you have your mobile phone, laptop, you have all package. It's solid state, And then you also change the valency of lithium and moving the ions, everything in this closed battery. What we do, we have an redox flow. The difference is that we have like an engine which converts these ions, and tanks is our capacity. Then size of the engine, size of this, let's say, stack with membranes and electrodes, determine how fast you can charge and discharge, and the tank size determine how much energy you can store. But you can have a small engine and store a huge amount of energy if you have large enough tanks. And this is also advantage over standard batteries, because this engine, it costs you most of the money, because then you have membranes, you have electrodes, this is where 70% of the cost, or maybe 80% of the cost is. And tanks and ions, the tanks are cheaper. Therefore, you can have large tank, like let's say 100 cubes tank, which stores so much energy. And then if you don't need much more per once, you don't need high peak power, you can slowly discharge it. Then you need a small engine, which engine in these terms means stack, membrane stack, or a redox stack, which you can convert this. Then it's a little bit different thinking. It's thinking in terms of engine, or the stack, how big will be the stack, and how big it's your tanks. It's like in your car, how big is your petrol, petrol tank. It means how far you can drive, how much energy you can store there, and size of your engine determines how quickly the power can be released. The same with redox flow batteries, the same with osmotic batteries, what I mentioned. And with lithium ion, it's a little bit different because it's closed battery or other type of battery, like lead batteries, lead acid batteries with old cars, then everything is in one device, an engine and the storage. Then the capacity mainly is given by the size of battery.
Yeah, where it makes economical sense to use a redox flow battery, for example?
I think everywhere where the storage time is greater than a couple of hours. If you look storage in days, then it makes sense. And also, if you want to, let's say, if you want to connect it to the grid for low storage, or maybe with wind can blow 2 weeks, and then maybe it will be 1 week no wind, then it's also good. Then my view, when you can apply this, then you need to store energy more than 1 day. And we need to also look at the storage, like vanadium batteries or redox flow batteries. They are relatively safe. They don't go on fire like ionic flow batteries. Then this is also why we are also interested in that they can stabilize the grids or stabilize mini grids, but also they are relatively safe. It depends on what ions you can use for this redox flow batteries, because some batteries are based on iron, some iron chromium, other vanadium, which is very developed, but they also look on for example, on organic redox flow batteries. They are not advanced now, but maybe they will develop them to more advanced systems. But we're looking more in environmental friendly way on this battery, especially in this other large application compared to lithium ions. As in the cars, you have some examples that if you overcharge lithium ion battery or deliver too much energy, it can go on fire,
Yeah. Then my last question, Piotr, it's a very long question, but it's like to wrap up what we have discussed. If someone new come to you, either end user, OEMs, or startup company who is building a membrane, okay. So what is the scope of Aqua Azure in terms of application and in terms of expertise? Is it the membrane, beyond the membrane, and application? I mean, you can check the box that we didn't check them in the discussion, let's say.
Yeah, then this is what we discussed. This is our scope. However, we also go beyond this. We want to accelerate innovation. The Aqua Azure, as it is now, we have expertise in these topics, what we today discussed. Ion exchange membranes, this energy from water, reverse electrodialysis, also for water, for hydrogen. However, we also do a lot for, let's say, accelerating innovation. Some companies, let's say, we are aiming for mid-sized companies, small mid-sized companies where we can accelerate innovations. And I have my, let's say, almost 10 or a little bit more than 10 years experience as CTO, where I have a feeling also how we can quickly improve, but also accelerate innovation in the company. This doesn't have to be membrane, doesn't have to be a flow battery, just innovation. We look on the company where it is now, where it wants to go, and how we can support them in terms of developing their products, their services, also their technology, but also from management side. I work with some partners which are very good from management and administration, and we together can basically, our goal is to bring the company to the next level. That if you have small companies, and especially technological company with a lot of, let's say, technical people, we say, okay, we can help you. We want to be very focused what we are doing now. We want this core business or core focus to narrow it and where you want to be in terms of your product services, and basically make a plan how to get there. And there's also an option that we support them. We step in and we support them. We support them with ideas. We support them with execution. And we can look on the, let's say, behind the shoulders, sometimes do, if they want, we also do and execute part of this assignment that we bring them to the next level. Always our goal is to bring them to the next level when they want to be, you know? And this expertise we also do. And this can be very broad, you know, from management to IP to technology to administration to production, many different aspects. But our goal is to next level, you know.
Yeah, I mean, super. Thank you very much. I can imagine, and I fully agree with you. It's unfortunately in the water space, there's so many know-how, but you cannot find them in books or in internet or somewhere. So it's in the people. It's in it only. Not few people, but so many people in the world that's really, as you mentioned, they can shorten your time more than even you think. I mean, I had experience when I was working in the past, was working with a consultant who teach me how to use the membrane, for example, in nutrition applications. It saves a lot of time, really, really. And it makes you faster to get to the markets, to understand the language of the end user, the language of the OEMs, and then to push the things forward.
Sometimes make connection, right connection, yes. Connect right product with the right companies to accelerate the speed. Then I was also, maybe as a side note, I was also working the startup spin-off from Unilever, Voltea, and we were developing our own product, membrane capacitive deionization. And I was working from R&D side. I was R&D manager to develop components. Later on, I was, technology manager to basically say, okay, this developed system, how we can commercialize. And I know whole process from, let's say, early development of materials and focus on IP to going via commercialization phase to the customers, and not always they are combined, because sometimes the engineers want to develop always better and better, but not always is needed. You know, you need to, as quickly as possible, validate your product on the market, learn from it, adjust. And this took us a lot of time. Therefore, I have all this learning from the startup, and I want to prevent this, that I want that the startups which comes to us, we can very quickly help, and as quickly as possible, they have a product on the market. They can validate, they can learn from it, you know, and then move on. And this is also our goal.
Super. Thank you very much, Piotr.
Thank you, Hakim. All the best. See you. Bye-bye.